Ever blinked an LED with Arduino? Chances are your first instinct was to use the delay function. It's simple, it works for basic stuff. But what happens when you want to do more than one thing at a time? Many Arduino projects need to manage multiple things happening concurrently. Maybe you want an LED to blink at one rate, while a buzzer plays a melody at another, and a motor gently moves back and forth. If you rely solely on delay, you'll quickly run into a wall. Imagine a waiter in a busy restaurant. If they took one order, then stood frozen in place until that single dish was cooked and delivered before even looking at another customer, the restaurant would be chaos. That's kind of what delay does to your Arduino. It makes the entire microcontroller pause, unable to do anything else. This can lead to missed sensor readings, buttons feeling unresponsive, and an overall clunky experience. The good news is there's a much better way. By understanding how to use the millis function for timing and by structuring our code into reusable components, we can achieve what feels like true multitasking on our Arduino. In this video, we'll demonstrate the pitfalls of delay, show the elegance of non-blocking techniques, and explore how to organize your code like a pro. You'll learn how to make your Arduino projects more responsive, more capable, and a lot more fun to build. Here's what you'll learn. Why the delay function can be problematic. How to use the millis function for non-blocking timing. How to create a reusable timer library. How to abstract program logic into a clean library. How these techniques enable complex, simultaneous actions. A glimpse into scaling things up with shift registers. Let's look at a simple example that highlights the issue with the delay function. Here's some code designed to blink 3 LEDs at different rates. We have a helper function called blink delay that works just like Arduino's standard blink example. We use digital write functions to set the digital output pin to high, typically 5 volts, then back to low, 0 volts, effectively turning the LED on for a set duration. We call the blink delay for 3 LEDs using different durations, slow to rapid. If you upload this to your Arduino, you'll notice something interesting. LED 1 will blink as expected, but LED 2 and LED 3 won't blink at their intended rapid rates. Instead, the entire program pauses for the duration of each delay. Let's break down what's happening in the loop. Blink delay is called for LED pin 1. LED 1 turns on, then the program stops for 1000 milliseconds. Then LED 1 turns off, and the program stops again for another 1000 milliseconds. 2. Only after those 2 full seconds of delays does the program move to the next line. 3. Then, blink delay on LED pin 2 is called, LED 2 turns on, the program halts for 200 milliseconds, LED 2 turns off, and the program halts for another 200 milliseconds. 4. Finally, blink delay on LED pin 3 runs, with its own set of 100 millisecond delays. Visually, you won't see 3 independently blinking LEDs. Instead, you'll mostly see LED 1 blinking slowly, and the other LEDs will seem to flicker erratically because their on-off cycles are constantly interrupted by the longer delays for LED 1. It's like trying to juggle 3 balls, but you have to freeze completely after catching each one before you can even think about the next. This is the core issue with delay, so it blocks the execution of your entire program. While the Arduino is in a delay, it can't do anything else. No reading sensors, no responding to button presses, nothing. So, how do we get around this blocking behavior and achieve true simultaneous actions? The answer lies in the magic of the millis function. Source code for this example can be found here or in the video's description below. The millis function is your new best friend when it comes to Arduino timing. Unlike delay, millis doesn't pause your program. Instead, it returns the number of milliseconds that have passed since your Arduino board started running. This allows us to check if a certain amount of time has elapsed without stopping the entire program. Let's rewrite our LED blinking example using millis. Here's the breakdown. 1. We store the last time each LED was toggled in start time. 2. In the loop, We get the current time using millis and store it in the now variable. 3. For each LED, we check if the difference between the current time, now, and the last toggle time, LEDs.startTime, is greater than or equal to the desired duration. 4. If enough time has passed, we toggle the LED's state, high-low, update the start time to the current time, and then move on to the next LED. The key here is that the loop function keeps running continuously. It quickly checks the timing for each LED and updates them as needed, without ever stopping. This is the essence of non-blocking programming. Think of it as setting multiple timers. You don't stop and stare at one timer until it goes off. Instead, you periodically glance at all your timers to see if any of them have reached their set time. We're essentially managing the elapsed time since the last action, rather than a fixed wait time. This subtle shift in thinking is what unlocks the ability to handle multiple tasks seemingly at the same time. Upload this code, and you'll see a significant difference. Now, all 3 LEDs blink independently at their specified rates. How does this work? Instead of telling the Arduino to wait for a specific duration, we're constantly checking if enough time has elapsed since the last time we toggled each LED. Source code for this example can be found here or in the video's description below. As your projects grow more complex, managing the timing for multiple elements directly in the loop can become a bit messy. This is where creating reusable components comes in handy. We can achieve this by creating custom Arduino libraries. If you have not created a custom library for Arduino before you can review this guide from the Arduino docs. Let's build a simple timer class to encapsulate our timing logic. The timer class encapsulates the millis, based timing logic in a reusable, object-oriented structure. It allows you to start, stop timers and check when a specified interval has passed, all without blocking the rest of your code. Internally, it keeps track of the last recorded time, previous millis, and compares it with the current time each time update is called. If the defined interval has passed, update returns true, signaling that it's time to trigger your timed action. The update function is designed to be called in the Arduino's loop. Now, let's integrate this timer class into our LED blinking example. The blink LED callback function is responsible for toggling the LED state from high to low or vice versa, and incrementing a counter each time the LED is turned off. Once the configured blink limit for that LED has been reached, the corresponding timer is stopped, effectively ending its blinking cycle. This separation of logic allows the timer to act as a scheduler, while the callback function handles the LED behavior itself. The start LED's blinking function resets each LED's state and counter, turns the LED on, and starts its timer. This prepares all LEDs to begin blinking again, each according to its own interval and limit. Since all timers are managed independently, each LED can blink at a unique rate and stop after a specific number of blinks without interfering with the others. An additional layer of timing is introduced through the use of restart timer, another instance of the timer class. Once all LED timers have finished, i.e., no timers are running, the restart timer is started. After its delay elapses, it triggers a restart of all LED blinking sequences. This demonstrates how the timer class can be used recursively or in layers, one set of timers managing per LED blinking and another managing the restart cycle, to orchestrate complex timing logic in a non-blocking modular way. What's cool here is that the timing logic is now neatly tucked away inside the timer class. In our loop, we simply tell each LED's timer to update. If the interval has passed, update returns true, and we can then perform the LED toggle. This abstraction offers several benefits. Reusability. We can use the timer class for any timing-related task in our project. Organization. The main loop becomes cleaner and focuses on the overall logic rather than the nitty-gritty of timing. Readability. It's easier to understand what's going on when the timing details are encapsulated. Testability. While not explicitly shown here, having a separate timer class can make unit testing your timing logic easier in more complex scenarios. This concept aligns with good software engineering principles, particularly the separation of concerns. The timer class is concerned solely with managing time intervals, while the main code handles the LED behavior. Source code for this example can be found here or in the video's description below. We can take this a step further and encapsulate the LED blinking logic itself into its own library. Let's create a new library called BlinkLEDs. All we have really done here is move the properties and methods out of the main Arduino sketch and included them in the library files. The logic that was in the setup and loop functions are moved into corresponding onSetup and onLoop function in the library. Now our main sketch becomes incredibly clean. The setup and loop functions are now just delegating to our BlinkLEDs object. This makes the main sketch much easier to read and understand. Even if you weren't concerned about reusing this LED blinking logic in another project, this level of abstraction improves the organization and maintainability of your code. It's perfectly okay to abstract code purely for better structure. Source code for this example can be found here or in the video's description below. The real power of non-blocking code and a well-structured architecture becomes apparent when you want to control multiple different types of components simultaneously. Let's imagine a project that involves blinking LEDs, playing a melody on a buzzer, and controlling a couple of servos. First, we'll need a way to play melodies. We can create a new buzzer melody library for this. The core logic is implemented in the playNote function. It uses the tone method to play a note in a sequence. It works with the timer library to wait for a given duration before playing the next note. Next, let's add control for a couple of servos in another library called servocontrol. The core logic is implemented in the moveServo function. It uses the servo.write method to move a servo 1 degree left or right in a sweep pattern. It works with the timer library to wait for a given duration before iterating to the next step. Multiple servos are controlled by the library, which can run at different speeds. Finally, our main sketch now looks like this. Now, in our loop function, we simply call the onLoop method for each of our components. Each component independently manages its own timing using our timer class and its specific logic. You'll see the LEDs blinking, the buzzer playing a tune, and the servos moving back and forth, all seemingly at the same time. This is the power of decoupling your code logic and using non-blocking techniques. Source code for this example can be found here or in the video's description below. What happens when you start running out of Arduino's digital pins? This is a common challenge in more ambitious projects. One clever solution is to use shift registers, like the 74HC595. These integrated circuits allow you to control multiple outputs using only a few pins. Let's create a ShiftLEDs library to blink 8 LEDs connected to a shift register in a ping-pong pattern, all without using delay. The ShiftLEDs class encapsulates logic to shift a single active LED back and forth across 8 outputs using a 74HC595 shift register. The shift-right function handles the low-level bit manipulation and communication with the shift register to turn individual LEDs on or off. The key animation logic is handled through a timer instance, ping-pong timer. The onSetup method initializes the hardware and kicks off the animation by turning on the first LED and starting the timer. In onLoop, the sketch checks if the timer has elapsed. If so, it turns off the current LED, updates the index based on direction go left, and lights the next LED in sequence. Then the timer is restarted. This separation of timing logic from animation logic allows the system to remain responsive and scalable, demonstrating the power of non-blocking timers in more complex I/O scenarios. And we update our main sketch. All that's needed is to add the libraries onSetup and onLoop functions to the main sketch. Now you can have your original 3 LEDs blinking, a melody playing, 3 servos moving, and 8 more LEDs on a shift register doing a ping-pong animation, all running concurrently and smoothly because we've avoided delay and structured our code logically. This illustrates that with non-blocking techniques and tools, like shift registers, the possibilities for simultaneous actions are virtually limitless, even on the humble Arduino. Source code for this example can be found here or in the video's description below. We've covered a lot of ground in this article, moving from the basic delay to a more sophisticated multitasking approach on Arduino. Let's recap the key takeaways. Never block the loop with delay. It prevents your Arduino from doing anything else during that time, leading to unresponsive and clunky projects. Embrace millis and elapsed time logic. This allows you to perform timing-based actions without halting the entire program. Abstract and modularize your code. Using classes and libraries for components like timers, LEDs, buzzers, and servos makes your code cleaner, more reusable, and easier to manage as your projects grow. Even for small sketches, adopting a clean architecture can be beneficial. It trains you to think about your code in a more organized way and makes it easier to expand later. By moving beyond delay, you've unlocked the potential for true multitasking on your Arduino, allowing you to create more interactive, dynamic, and impressive projects. I encourage you to experiment with these techniques in your next Arduino adventure. Think about how you can break down your project into independent components, each managing its own timing. You'll be amazed at how much more your Arduino can do simultaneously. Ready to take your Arduino skills to the next level? Why not grab all these libraries and examples and start playing around? You can find the code for all the examples discussed in this article in the video description below. Happy making!